Hi, well, this is Adam Abraham, and today we're going to talk about surface tension relative to structured water. When water is in a structured state, you can expect that its surface tension, that is, the amount of force that is required to break the bonds of the water molecules, is going to be reduced. And when that happens, it means everything. Now, why is it important? It's important because there is a body of, let us say, belief, scientific belief, I'd even say, that suggests that the only way to lower surface tension is through some form of chemical input. The term typically is called a surfactant. And, well, if that's so, I mean, that's one reason why you have salt, you have water softeners, for example, that require some kind of input, such as some form of salt, for example. And yet, many communities, because of the imbalance that those systems are creating in the ecosystem, they're starting to, well, say, no, can't do that. Well, there must be another way of doing it, and as it turns out, there is. The Rainmaker devices, our Rainmaker technology, will reduce surface tension significantly, and without any chemicals, without any other inputs other than the energetics, the effect of the energetic, let us say, influence that the device creates inside the chamber as the water passes through. Now, this is going to be part one of, say, a two-part video. This one, we're going to just talk about surface tension, and for that, I have asked my friend Douglas Harkey to talk a bit about what it is, explain it, and we have some interesting demonstrations. The second part of this video, and we talk about it as this one goes on, is my colleague Joseph Johnson is actually going to do a test where he is running water and comparing surface tension of water passing through, well, base water, first of all, and measuring the surface tension. And then he will compare that to the surface tension of water that passes through the Rainmaker unit. So anyway, here's my friend Doug. Take it away, Doug. So why is surface tension important? What is it and why is it important?
Well, surface tension has to do with the, let's see if we can talk about it in layman's terms. It's the electrostatic charge that's on water.
Yes.
But what's that mean? Mm-hmm. We say H2O all the time, but we don't think about two hydrogens particularly, and we don't think about oxygen, mm-hmm. and how they're bonded and how they're bonded together in a particular way. When the hydrogen is bonded to the oxygen molecule, the hydrogen is positive. So it has a polarization, mm-hmm. so a positive and negative. So you're thinking about water like a magnet. And when the water molecules are in a droplet of water, I don't know if you can see this, but it's sure easy to drop a water on anything. Instead of just running super flat, it sits up like a bubble. Mm-hmm. And the bubble is created by the water molecules bonding together. Mm-hmm. So I'll slip into kind of normal language, and then I'll slip into scientific language to try to explain it.
And one other thing, though, you mentioned an electrostatic charge. Mm-hmm. Now that suggests electricity, but it also suggests attraction. Okay, so we're talking about a draw or repulsion. Mm-hmm.
Here's a little magnet. Mm. I drop that, of course, it's attracted because there's a positive side of the magnet and a negative side of the magnet. When I reverse the polarity, it wants to push away. That's such a wonderful little expression of magnetic forces just playing with a little magnet. But water's the same way when it's charged, and water's always charged because it's positive and negative. So water, because there's lots of molecules of water, they clump together, and the hydrogens clump together like a magnet and create, in many cases, let's say a tetrahedron, so like a pyramid.
Right.
And they call that being cohesive or an attraction. So the real word is it's being cohesive and it's attracting. And when all those things attract, it creates a little hump in the water, a little surface, almost like elastic.
In other words, there's a tendency to hold together. Yes.
And they call that surface tension because those water molecules are bonded together and it creates a surface.
Also, the pressure isn't as equally distributed at the surface of the water, where it's next to the atmosphere, as it is under the surface, where it's just water molecules all around.
I can take pennies, and I'm just trying to make sure that you can see that we're just messing around with water. That's just water, and I've poured it into this little glass, and I've topped it off. Then I can just drop endless pennies in here. Oh, not endless, but I just the water is building up a dome as I drop the pennies in. See, I'm just pushing to the surface. And see how now it's got a big dome. I can keep on dropping pennies to the surface without, and it's just about to run over. I'm just about to, it's still hanging in there. Oh, there it went. I finally busted the dome and it spilled over the top. But that's a cohesive force, because the water molecules have bonded together. They call it if I'm saying it right, I'm trying to think of it, Cohen effect. It's just the effect of the electrical molecules hanging together. And you get the surface tension. Now I'm going to dump out all those pennies, and we're going to add water back in. Get that little dome on there. Now I'll put a piece of paper on top of it. That has to do with the surface tension and the atmospheric pressure in the room. And that's holding the water in the glass. If I had a piece of mesh over this, I could pour the water right straight through the mesh and then turn it over again, and the mesh would support that water. But as soon as you turned the angle, that would change and it would pour right through the mesh. So that would be a very, very good way to test the surface tension of the water, and if you've broken the surface tension of the water. If I put a little bit of Dawn dishwashing detergent on it, that breaks the surface tension of the water molecules, don't bond, and then it won't do that anymore.
Right, and they call that a surfactant.
A surfactant.
Essentially, essentially, it makes the water molecules smaller. Essentially, is that correct?
Or they doesn't make them smaller. It makes them so that they're not adhering anymore.
Got it. It breaks the bonds.
I guess if you think of it as a ball of clay, yes, you're separating the ball of clay, and now there's less things clumped together, so now it goes right through the mesh.
So in other words, the materials that's in the surfactant, that's in, say, Dawn, for example, which are other elements, so to speak, they themselves also have charges, and then they start to interact with the molecules of water, and so they start to attract and gather there, and it starts to break. It breaks the water molecules up, the cohesiveness of it, etc. But therefore, the surface tension of the water is reduced.
Right. So surfactants create a situation where you can get a plate cleaned because the surface tension is broken, and you can get the plate cleaned. So it really does have a lot to do with our everyday life.
Sure, sure. Now, there is a body of belief, or I'd say, I'll call it belief, in certain realms of science, for example, that presume that the only way to change or reduce surface tension is done by chemical means. And we are seeing a phenomenon wherein by creating a structure in the orientation of the water molecule, we're seeing the same effect. We're seeing a reduction in surface tension. Okay.
And when you have a reduction in surface tension, that'll change how much water you need for the plants, and also change the exchange of proteins on the roots below the soil surface. And it helps the plants pick up more nutrient. You get a more robust, lively plant, and when you have a lively plant doing all of its biofunctions, it's disease resistant. Disease has a purpose. The purpose is to take out the weak plants. If you have a robust, healthy plant, it's disease resistant and it gets an abundance of fruit. And that all has to do with the exchange of proteins via the water. So structuring the water is super important, and knowing what you're doing intentionally could be tremendously beneficial.
Now, we have done a test. In fact, before I came over here, it was still uploading, so you really actually haven't seen it, of a video where we are taking water, one of our associates is taking some water, tap water, I think some RO water, etc. He's measuring surface tension with an instrument that measures the Dyne. It's described in terms of Dyne, and it's a measure of the amount of pressure and force that is needed to break the tension. Okay. Typically, our tap water would have a Dyne rating of about 72.
Okay.
Somewhere in that around, in terms of amount of grams per something, etc., of force in order to break the surface tension. Well, hydration tends to occur at a level somewhere under 50 dynes. Okay, so within the water there needs to be enough happening that has a sufficient amount of water that is at that lower amount from a hydration standpoint. And what we have demonstrated by pouring water through, and literally just using gravity, pouring it through one of our Rainmaker devices, is, and just using gravity now, at least 10 dyne reduction in the amount of force. Okay, and that's just using the gravity. Not even putting it under pressure, because we're figuring when it flows naturally under pressure, there's going to be even greater action, so to speak, in that respect. But this is with no chemicals, just simply the materials, the motion, the dynamics, as well as the paramagnetic effects of some of the materials that are in the unit that the water is going through.
It's amazing to me that two effects that are around us constantly, which would be electromagnetism and water, are both two things that we know the least about.
True.
Water and magnetism. And it seems to be the hot topic right now, is people studying and working and digging towards magnetism and the nature of water.
Well, you commented, in fact, one of our impromptu videos about rainwater as literally being magnetic and having magnetic properties to it.
You'd probably think of it as static electricity.
Yes.
And when you have water that's falling and tumbling, it's picking up a static electric charge. Okay. Because of what it is. And as a result of that static electrical charge, it also becomes somewhat magnetic. Electricity is magnetic by nature. So if you have a static electric charge on the molecules, and the molecules also having a positive force back and forth, that's makes it magnet. That is magnetism.
Sure, sure. Well, it's a thing. It's attributing a property to water that typically is not. We only tend to think of water in terms of wetness, and we don't even think of it as that. We don't think of that wetness as being variable, you know, relatively speaking. And the amount of wetness or the variability comes back to surface tension. How absorbable is this water? How easily does it get to where it needs to go? How permeable is it?
Well, it'll lay on the leaf differently.
Yes.
It'll lay on the roots differently. It permeates the soil differently as a result of its structure. And so paying attention to how to structure water is an important aspect.
Oh, wow.
It can't be ignored. It shouldn't be ignored. It's been ignored for a long time.
All right. Well, we're bringing some light to it, and
we are.
and showing that there are practical, everyday reasons. I mean, even just a simple process of taking a shower. If the water has, you could say, structure to it, if it has lowered surface tension, it basically means you use less soap.
Right.
You get actually more absorbed in it. I should say more is absorbed within you, because a lot of people think that we have a skin, and therefore the water just bounces off us. We don't think of it, the fact that we're actually absorbing water, our content, just by taking a shower or taking a bath.
It's interesting. You can take a little stick of wood and carve it into a boat, and put a piece of just put a dab of glue on the back of the boat and set it in the water, and it will propel it forward as it breaks the surface tension. So
wow.
It's a force.
Wow. It will move simply on its own.
It'll go just
perpetually
until the glue dissipates.
Wow.
It's breaking the surface tension of the water and pushing the boat forward. It's
fascinating.
Yeah, it's an amazing. Water's so amazing.
Yes, it is. Doug, thank you very much.
You're welcome.
Well, I hope you found that to be informative, and it actually kind of begins to show you how important this apparently simple phenomenon actually is. It actually means very much everything, and it's not a simple task to create this change, this very important change, without creating any additional harm. But the Rainmaker technology manages to do it. Anyway, let's go on to video number 2.